Our AI roams around freely, exploring its surroundings and enjoying nature. Suddenly, it detects something, an enemy. The enemy is out of sight, hiding in the shadows. Instantly, the AI switches from roaming mode to chase mode. It hunts down the enemy and eventually catches and eliminates the threat. With the danger gone, our AI goes back to its original task, roaming. But how do we program such behavior? How do we make our AI know when to roam, when to chase, and when to attack? One way is to use simple if-else statements. We could check if there's a target and if that target is within range. But as our AI's tasks grow more complex, these conditions become harder to manage. Imagine adding behaviors like stealth movement or team coordination. It quickly becomes a tangled mess. This is where a state machine comes in. Think of a state machine as a set of rules that define different states, like roaming, chasing, and attacking, and how to transition between them based on certain conditions. It's a clear and organized way to manage our AI's behavior. In a state machine, each state is like a mode of operation, and the AI knows exactly what to do in each mode. When a specific condition is met, it smoothly transitions to the next state. Simple, efficient, and easy to expand. This is the power of state machines. All right, let's dive back into our code. Since we'll be accessing the Fort character, navigatable, and focus interface multiple times, it's a good idea to extract that functionality into a separate class for ease of use. I've named the class Guard AI and included all the necessary member variables. Now, it's time to implement our state machine. We'll be using a simple state machine built with an enum and a switch case expression. Here's the enum with 3 states: roaming, chasing, and attacking. To keep track of the current state, we store it in the Guard AI class under the variable Guard state. We also need to create an instance of our Guard AI class, but since the guard hasn't spawned yet, we store it as an optional and fill it later. In the spawn function, we'll assign the newly spawned guard. Next, we need to implement our custom state machine function. First, we retrieve our newly spawned guard and check if they're alive. Based on the current state of our guard, we'll execute the appropriate state function accordingly. Now, let's implement our state functions. The roaming function already exists, so we can use it as it is. Next is the chasing state function. This function will take our guard AI as a parameter, but since we haven't implemented it yet, we'll leave it empty for now. We'll do the same for the attacking state. Since both the chasing and attacking states take guard AI as a parameter, to keep things consistent across all states, we'll modify the existing roaming function to match this interface as well. Both our chasing and attacking states require a target. So, how do we get one? If you remember from part 1, we use the onAlerted function to acquire a target. Since we're no longer using it directly, we'll store it as a variable for use later. I've created a new class for our target, simply called Target. In this class, we'll store the agent and the Fort character as well, since we'll need both later on, and we store ours optional target here. Now, let's revisit our onAlerted function. We'll clean it up by removing almost everything, except for the essentials. We need to retrieve the Fort character of the target and our guard AI. After that, we can set our optional target for future access. When the guard is alerted, it means we need to switch to the attacking state. To make state transitions easier, let's create a helper function to handle this. In our guard AI class, we'll add a new function called change state, which takes new state as a parameter and returns nothing. We'll only change the state if the current state is different from the new one. Now, let's go back to the onAlerted function and use guard AI to switch to the attacking state. Now, it's time to implement our attacking state. First, we check if our guard is still alive, then verify if we have a target, and finally confirm if our target is alive. Do you remember from the previous tutorial? To make the guard attack, we need to control its vision using the focus interface and the maintain focus function, passing our target's agent as a parameter. However, right now, our guard only looks at and shoots the target without moving, which makes it an easy target. To fix this, we need the guard to move unpredictably, something like a zigzag pattern. But before introducing that feature and quickly test our code, I'll temporarily borrow the roaming code and paste it here, changing target to nav target to avoid conflicts with the target parameter. Now, we can call it in this context. However, there's a problem. Did you notice it? Take a moment to figure it out. The issue is that the maintain focus function runs first, and only after it finishes does the zigzag movement start. That's not what we want. We need both actions to run simultaneously. To solve this, we'll use a race expression. This means both actions will start at the same time, and if one completes, the other gets cancelled. Just like in a race, only one winner and the rest lose. Now let's move on to the chasing state. As usual, before doing anything, we need to check if both our guard and target are still alive. Since we want the guard to respond immediately when spotting a target, we need to ensure that his eyes are always fixed on the target. To make the guard chase the target, we pass the target's agent as a parameter to the makeNavigationTarget function. But just like in the attacking state, we want both actions, focusing on the target and chasing it, to run simultaneously. So we'll wrap them in a race expression. One thing to note, this function isn't a suspend function, so we can't use it directly here. Instead, we'll use a block expression to group the two actions together and ensure they run at the same time. Now, let's scroll up to our runStateMachine function. As you can see, it only runs once. To make it run continuously, we'll wrap it in a loop expression. However, each of our states takes a long time to run, and by the time the loop starts again, we don't know if our guard is still alive. So, we need to check that every time before proceeding. But there's a big problem. As you can see here, we get a runtime error due to an infinite loop. The loop runs over 100 million times. That's a massive number if you ask me. This bug is incredibly rare, and it never showed up when I tested on my private island. It only happened a few times on public islands, like 3 times here, 1, 1, 2, and so on. It took me countless hours to figure this out. So, what's the problem? When we check if the guard is alive, if it's not, this function doesn't suspend and just keeps checking, leading to over 100 million iterations before it crashes. The lesson here is, whenever you use an if statement inside a loop, always make sure there's a way to exit the loop. In our case, using else and break is enough. That way, if the guard is eliminated, we exit the loop. Finally, our state machine isn't running yet. We need it to start right after the guard spawns, so we'll call it in the onSpawned function. But how does our runStateMachine function know when to switch to a new state? We need a signal to indicate that the state has changed. To achieve this, we'll implement our own event. We'll store this event in our guard AI class and name it stateChangedEvent. Inside the changeState function, right after changing the state, we'll broadcast this event by calling the signal function on stateChangedEvent. Next, we need to wait for this signal using the await function. However, there's a problem. Currently, the state waits for the signal first and then runs the state's logic. That's not what we want. We want the state to run and wait for the signal simultaneously. To solve this, we'll use a race expression again. But there's another catch. A race expression requires that all expressions inside it are suspendable functions, and in our case expressions are not. So, we'll extract the state logic into a new function called runStateOnly, like this, and call it within the race expression. Alright, the technical stuff is done. Now it's time to add some visuals and make things fun. Let's switch back to UEFN and create a playground with some cover and hiding spots so we can really put our shiny new AI to the test. And hey, let's build another red versus blue map. Just kidding. Something simple like this will work perfectly for our test. So, hit that launch session button, and I'll meet you on the battlefield. Okay, I've got to be honest. I may have lied. I did some testing and we're missing a few pieces. Right now we're only using 2 states, attacking and roaming. We set roaming when the guard spawns, and we switch to attacking in the onAlerted function. But what about the chasing state? Can you guess where that should go? Yup, it belongs in the onTargetLost function. Just like the onAlerted function, this one also gives us a device AI interaction result, where the source is the guard and the target is us. So we can yoink some code from onAlerted and paste it here. But when a target is lost, 2 things could have happened. Either the target moved out of sight and found cover, or they got eliminated by someone else. So we need to check if the target is still alive before moving forward. Luckily, getFort character is a deceivingly helpful function. If the target is eliminated, it fails the check automatically. We'll move the check down here. If the target is still alive, we'll store it as the new target and use guard AI to switch to the chasing state. Otherwise, if the target is eliminated, we'll clear it and switch the guard back to roaming. Now let's talk about the onUnaware function. This means our guard feels all safe and sound, so it switches back to roaming mode and, clears all the hatred. In other words, it clears the target. Next up is the onEliminated function, but we haven't used it yet, so let's skip ahead to the onEliminating. This means the guard has successfully eliminated the target, mission accomplished. With the enemy down, we switch back to roaming. Alright, let's go find our lovely guard, shall we? Oh, look at that. Quick, let's hide over here. Wait, check it out, he's chasing us. How about we try a longer distance? Wow, still going strong. Oh man, he's so fast. Run, run, run. Hold on, I found a perfect hiding spot. Ha, he can't find us now. That means he's unaware and switched back to roaming. Nice, our state machine passed all the tests. How about we re-engage for another round of combat? Boom, still working perfectly. Now, let's talk about making our code a bit safer. Did you notice in the roaming function we're using a loop? That could be a sneaky spot where a runtime infinite loop pops up. You might be thinking, nah, it's fine. But hear me out. The navigate function is a suspend function, and it gives us a navigation result. In my experience, if our guard gets eliminated during roaming, things can get messy. The navigation might throw an error immediately, and the loop could keep running, hanging there, wasting precious resources. So it's always a good idea to exit the loop if an error happens. Just like before, we'll check if our guard is still alive before moving forward, something like this. And the same goes for our move zigzag pattern too. Oh, and speaking of the move zigzag pattern function, do you think now's the best time to implement it? It's going to be a pretty math-heavy function if you ask me. But before we dive into that, I've got something interesting to show you. This device can only store and control one guard per device at a time. Is that a limitation of our AI behavior? Well, kinda. But there's a way to improve it, so it can handle multiple guards on a single device. Now, why haven't I implemented that here? First off, it would complicate the tutorial and make things harder to follow. And second, you might not even need it. Here's why. In the device settings, you can only choose one cosmetic skin per device. That means if you spawn multiple guards from the same device, they're all going to look identical. And let's be honest, a game where all the guards have the same skin? Boring, right? But if you're sitting there thinking, no way, I want it. Well, no worries, I've got you covered. We'll tackle that in the next tutorial. Until then, see you soon.